Hello, welcome to IB Physics 8.3 review, energy, work, and power by me. So, here's the table of contents, and let's do energy. So, conservation of energy, what is it? Energy is not created or destroyed, only converted from one form to another. So, in an isolated situation, the total amount of energy is constant throughout. And what is inelastic versus inelastic collisions? So an elastic collision means that the initial kinetic energy is equal to the final kinetic energy. It's conserved. Whereas an inelastic collision means that initial kinetic energy is greater than final kinetic energy, meaning somewhere along the collision, the kinetic energy was converted or lost due to dissipation, maybe to heat or friction. So what is energy? Energy is a scalar. It's by definition the ability to do work, and it exists in many forms up here. Its unit is joules, and that's equal to kilograms times meters squared over second squared, and that is derived from the units for this formula: 1/2 mv squared, which represents kinetic energy. And kinetic energy, I think of it as just movement. Whereas potential energy, I think of it as the potential force if something fell from this height. And the formula for potential gravitational energy is mgh. These two are arguably the most important formulas you would need for this test, I think. And mechanical energy is the combination of these two in a situation. And throughout a scenario, ideally, the mechanical energy should be conserved if no non-conservative forces acting on it. And non-conservative forces just means basically external forces. But more on that later. So let's do this question real quick. So knowing that the mechanical energy needs to be constant throughout the entire scenario at every point, we can equate, if we want to find the velocity at point P, we can equate these two mechanical forces together. And we know that since at the top the car isn't moving, it has 100% potential gravitation energy, then we can find the potential gravitation energy here because it's not moving. 1/2 mv squared. If v is 0, then the whole thing is 0. So 100% mgh, which is, let's see, mass is 1, and then gravity is, let's say, 10, h is 45. So 450 is our total mechanical energy at each point because it's here. And at point P, it's 30 meters or 30 cm above the ground. So we can find our mgh first. So 10 times 30, 300, and again, mass is 1, so we can just times 1, and plus x, which is kinetic energy at this point. So 300 is the potential energy at this point, plus x is the kinetic energy. So this total is mechanical energy at P should equal 450. Again, mechanical energy is the same at each point. So x is 150, and we can equate the kinetic energy formula to 150. So 1/2 mv squared, and again, m is 1, so v squared is equal to 150, and v is equal to the square root of 300. So now, what are conservative versus non-conservative forces? So conservative forces are forces where the path you take to get to point A to point B does not matter. It's the same regardless of what path you take. For example, if you're walking upstairs or walking downstairs, let's say, from third floor to first floor, you gain some amount of potential. You gain some amount of energy. Whereas, if you jump from third floor to first floor, you also get the same amount of energy transferred to you. So the work is the same, but the time which it took is different. But regardless, the work is the same. And that's a conservative force. Whereas an non-conservative force, its work depends on like the distance you actually traveled, not just displacement. For example, from point A to point B, if you take this straight line, and let's say you're in a car, you take the straight line, you get some number of some amount of friction that acted on you. But if you take this curvy line, you get even more friction acted on you because you drove a longer distance. So this is like a non-conservative force. It changes based on the actual distance, the path you took to get from point A to point B. And examples are friction, drag, applied force. Yeah. So a varying force is a force that changes magnitude, direction, or both over time or position. And an example of this is like a spring. Like depending on how far you pull it back, the position, your magnitude changes, because the further you pull it back, the stronger potential energy it has. And to know what to know for spring forces is Hooke's law. K is the spring constant, X is extension or compression from rest. And the change in elastic potential energy or potential spring energy is equal to 1/2 spring constant K times delta X squared, where X is the extension and this is this basically. And this would be what a graph looks like. As extension increases, the force increases as well. And also there's a point at which you pull too much and the spring deforms. It looks something like this, and this point is called elastic limit, and after the elastic limit is reached, the spring is deformed. Work is also a scalar. It's basically energy transferred over a distance, and the units is in joules because, again, energy and work, they have the same units because it's just transferring it. And positive force, positive means like, so basically work can be positive, 0, or negative. Positive mean that force and the direction of displacement are the same, pointing the same way. So say you push a box this way with this much force, and then the box moves this way, then you have a positive work. A 0 work is achieved when the force and displacement are perpendicular. Oops. Okay. Perpendicular, or you push a box but it doesn't move. In the first situation where it's 0, it's because the cosine of 90 degrees is 0. So basically your horizontal component would be 0, and anything times 0 is 0, regardless of how far it moved. And then the second scenario here, even if you push it with 1,000,000 newtons, if it doesn't move, then your displacement is 0, and anything times 0 is still 0. The work can be negative if your force and displacement are opposite of each other. Like this. Yeah. So you push it this way, but it actually moves that way. That's negative force. Or not negative force, negative work. And basically work is displacement times force. And it's important to note that force means collinear to the direction of movement. So let's take a look at this example. So we have a box moving this way, d distance. Say this angle is 60 degrees, and this force is 10 newtons. So if we want to find the collinear force, we need to find the horizontal component of this force. And that would be cosine theta times the magnitude. So 10 cosine 60 times displacement is equal to our work. And that's, just keep in mind, if there's like, if a force is applied at an angle, find the collinear force to the direction of movement. And for another thing is, when looking at a force times displacement graph, if you want to find work, it's basically just the area under it. And say you want to find work from one point to another point, A to B, it's just the area under that section. Just use simple geometry. Yeah. Next, the work energy theorem. So net work is basically equal to changing kinetic energy, like these. And changing kinetic energy, that's basically the net force times displacement, because your force is changing. Yeah. So work net is equal to net force times displacement. This is important to know, especially if you have a free body diagram. It's the net force times displacement is equal to your net work. These are a bunch of equations that I saw on the slideshow, and I don't really remember them, so maybe it's important to remember these. I'm not sure though. So net work is equal to, this means the work done by a conservative force, as we said before, conservative regardless of path, non-conservative depends on path. Yeah, so the net work is equal to conservative work plus non-conservative work. And next, the net work is also equal to delta, change in kinetic energy. And then the work of the conservative forces is equal to negative delta potential energy, so negative change in potential energy. And this one was highlighted, so I assume it's important. Let's see. So the work of a non-conservative force done by non-conservative force is equal. The work done by non-conservative forces is equal to change in kinetic energy plus change in potential energy. I hope the test doesn't have something like this. This is weird. Okay, so power. It's a scalar again. So energy, power, and work are all scalars. How much energy, it's basically how much energy is transferred over a time. So think of like a punch versus a push. A punch has more power because like you transfer so much energy in so little time, whereas a push, you transfer some energy over a longer period of time. So that's basically what power is. And power is work divided by time or energy divided by time. These can be used interchangeably. And if the force acting on it is constant, you can use force times velocity, because basically force times velocity is equal to force times displacement over time, because meters per second. Yeah. So this is basically work over time. It goes back to this. Let's see. Again, this is what it is, and its unit is in watts. And these are the derived possibilities. And be careful that Mr. Gannon might ask something like this on the test. So basically, power can be negative if energy is being removed from a system. For example, like a car that's going at some velocity suddenly uses its brakes. The brakes are have like negative power on the car because it's taking away its energy. Let's do this example question. So Captain Cool runs his 10 kilo means 1,000, by the way, and mega means 1,000,000. So it's important to know. 10 kilowatt refrigerator for 3 hours continuously. How much energy does he use? We have the power. We have the time. So we can use this equation because we're trying to find energy. So P, so 10 kilowatt, 10 times 1,000. 10,000, because the basic SI units are in watts, is equal to energy, which is the E, over time, which is in seconds for the SI units. So 3 hours, how much time is that? let's see, 60 seconds in 1 minute, 60 minutes in an hour times 3. So 3,600 times 3 times 3. This much seconds. And then you multiply this onto this side, and that's how much energy you need. Okay, efficiency. So it's basically measuring how efficient an energy transfer is. It can be measured in work, energy, or power. And the formula is efficiency is equal to useful over total. It's always, so let's say E for efficiency is always going to be between, I don't think you would have 0 efficiency because that basically means you get nothing. And what's the point of that? So, and 1. And theoretically, you could have 1, but it's physically like impossible to have an efficiency of 100% because a lot of energy is lost to heat as heat. It can never be greater than 1 because that would imply that you gained energy somehow, and that violates conservation of energy. So let's do this practice problem. A cruise liner running on diesel has fuel of this much, a fuel power of this much. So this is power. And it contains about this much, the fuel contains this much energy per liter. Engines have 25% efficiency. How much fuel must be carried? So we have power, we have energy. And by the way, 25% efficient. So we have 44 total. And if it's 25%, then it's 11 actual usable megajoules of energy. So we have this much and this much, and we have time. So we need to find actually how much energy we need total. So 337 times a million. So what was that? 6 times 10 to the power of 6. Is equal to total energy, say E, divided by time, which is 24 hours. Oops. 60 seconds in a minute, 60 minutes in an hour, times 24. And then we would, let's see how much that is. Okay, I got like 3.19. Let's say 3.2 times 10 to the power of 12. This is how much energy you would need, and you divide this by 11 times 10 to the power of 6, because that's actually how much energy you get per liter. And then you would get like, let's see. You get 290,618.2. Yeah. That's how much fuel you must need. And a Sankey diagram, it's pretty easy. It's just a representation of how your system transfers energy. So say a hairdryer, it's electrical energy, and the pointing right is basically your useful energy. Pointing down or up is basically useless energy. It must be to scale, of course. As you see, 550 is a lot bigger than these two, and it's bigger than these two because it's to scale, and it has to have units and labels. This is pretty easy. Yeah, that's Sankey diagram. Goodbye. Good luck on the test. Let's manifest a 7.